In this video, we're going to tackle about energy and laws of thermodynamics. Now let's proceed. Okay. Now we're going to define energy. Energy is the quantitative property that must be transferred to an object in order to perform work on or to heat the object. Hence, it is the application of heat to a certain system to do work. Now, heat is a particular form of energy that is transferred from a body of high temperature to a body of cold temperature. Now, we have the following conversion of units. The first one is for pressure. If we're going to define pressure, it is the force exerted per unit area. Now, an atmospheric pressure or ADM is equal to 101,325 pascals or PA. It is also equal to 1.01325 bars, 14.7 psi or pound force per square inch, 760 millimeters mercury. Now for a Pascal, it is equal to a Newton per meter squared or 1 N per m squared. A bar is equal to 100,000 pascals. And for energy, the SI unit for energy is in terms of joules. And for CGS, it is in terms of ergs. Now for English, it is in terms of BTU or British Thermal Units. Now let's proceed with the following conversion units for energy as a joule now is equal to a Newton meter or a kilogram meter squared per second squared. And a joule is equal to 1 times 10 raised to 7 ergs. Okay. When we say ergs, this is in terms of a gram centimeter squared per second squared. A BTU is equal to 1055 joules, and it is also equal to 10.409 liters atmospheres. It is also equal to 252 calories or cal, and a BTU or a British thermal unit is also equal to its FPS as 778 feet pound force. A calorie is equal to 4.184 joules, and a kilocalorie is equal to 4.184 kilojoules or 4,184 joules, and a feet pound force is equal to 1.356 joules. A feet pound force per pound mass is equal to 2.9890 joule per kilogram. Now let's proceed the third parameter as your power. Power is the energy per unit time. Okay, as you can see here, a watt now is equal to a joule, which is the SI unit for energy per unit time as in terms of second. Again, 1 watt is equal to 1 joule per second. And a horsepower is equal to 746 watts. The fourth parameter is your gravitational constant, GC. Now we have different values for gravitational constant in terms of SI and FPS or English units as the following. For SI unit is equal to a kilogram meter per Newton second squared. And for the English or FPS, this is in terms of 32.2 pound mass feet per pound force second squared. Now let's proceed with the three statements for thermodynamic laws. The first statement, okay, which is the first law of thermodynamics, it is the law of conservation of energy, which states that energy can neither be created nor destroyed. Rather, it can only be transformed or transferred from one form of energy to another form of energy. Now we have the following examples as The following we have exercising, jogging, appliances, rest, two moving automobiles, photosynthesis, power plants, and smartphones. Okay. For exercising and jogging, your potential energy and stored kinetic energy is converted to kinetic energy once you are moving. And then when you are exhausted, your kinetic energy or excess kinetic energy can be converted to high temperature or heat. Now we have your appliances. It depends now with the use of appliances. Say, for example, we have your smartphones, okay, from electrical energy, which is stored in the battery. Once you're going to use your smartphones and you're going to turn it on, your electrical energy will be converted to light energy. And once you overuse your smartphones or after a certain long period of time using your smartphones, okay, your light energy now would be converted to heat energy. Okay. Now we have your photosynthesis. Okay. If we're going to take your leaves as the system, it absorbs solar energy. And then within the leaves, the solar energy now will be converted to chemical energy. Okay. Then we have your power plants. It depends now if we're going to tackle about geothermal power plants. We have your heat energy, which is converted to mechanical energy and electrical energy. Now let's tackle the second law of thermodynamics, which states that the state of entropy of the entire universe as an isolated system will always increase over time. It is impossible to construct a device operating in a cycle which works on a single heat source and converts all of its heat completely into work. Heat cannot itself flow from colder body to a hotter body. Again, heat can only flow from higher body to a colder body. Okay. Now we have the following examples for the law of entropy for the second law. The first one is air leaks from the balloon on its own. Okay. As you can see here, when we say entropy, it is actually the degree of disorderliness. Okay. From disorder or inflated order or form of your balloon, as the air leaks now, it will deflate into this form. Take note, entropy is the degree of disorderliness. From this first state of orderliness, which is the inflated form of the balloon, and then converted to deflated form of the balloon. Okay, so that is very disorder. Okay, and take note that as air leaks from the balloon, air escapes the balloon and it never re-enters within the balloon. The second one is we have two gases will mix automatically on its own. As you can see here, the initial state of the container, we have gas particles in red, which are the hot ones or the hot gas particles. And then we have the cold gas particles in blue or on the right side of the first state. If we're going to lift now this boundary, okay, the gases will start to mix on its second state. Okay, so this is spontaneous process as the gas will mix and will it will equilibrate to a temperature. Okay, this is a continuous process within the container. So this is actually a second law of thermodynamics. Now we have the cooling coffee, okay, escaping of heat from hot coffee to a colder reservoir. Okay, and then we have the ice melting, moving of heat to the ice itself. So the ice melts. And then we have water. Okay, water flows from an elevated tank. Then we have the following applications on cars, bike engines, and refrigerators. Okay, so see according to the Kelvin Planck statement, there should be at least two thermal reservoirs, one at higher temperature and the other one at lower temperature. Then only the engine will work. Okay. So for the car, bike engines, and refrigerators, we're going to consider two thermal reservoirs. The movement of heat from a higher temperature to a lower temperature. Now that are those are the examples for the second law. Now let's proceed with the third law of thermodynamics as concerned with the limiting behavior of systems as the temperature approaches absolute zero. The third law also states the entropy of a perfect structure. Okay. So we have your crystals is zero when the temperature of the crystal is equal to absolute zero. Another statement for the third law of thermodynamics is two objects are in thermal equilibrium or same temperature. Now we have the last as your energy efficiency. The most efficient according to the Wall Street Journal is the wind energy because it doesn't emit any carbon dioxide or any harmful gases. Okay. So the ones are the most non-sustainable energy sources as your coal, oil, and natural gas. Okay? The most efficient is the wind, followed by geothermal energy. And then the third one is your hydrothermal energy. The fourth one as your nuclear energy. The fifth one as your solar energy. And then we have the sixth one as your biomass. And then the seventh, eighth, and ninth goes to natural gases, oil, and coal. Now that ends my presentation. For my next video, we're going to tackle about the different sample problems for the laws of thermodynamics, and we're going to proceed with the calculations for electrochemical cells.